Back again with more curve sketching for your calculus A, B, and BC work. So let's take a look at this is section 5.3 concepts worksheet. So the idea here is to produce a graph that follows the properties given here. Let's take a look. So we've got f of negative 2 equals f of 7 equals 3, and I think I'm going to just put those points in right away. We also got f of 4 equals 3. The roots of f of x equals 0 occur only at 0 and 6. So let's put those 2 points, 0 and 6. Okay, and now for each one of these, we have some information about concavity and slope, which will help us. So between negative 2 and 0, we have positive slope, and we have a negative concavity. And then when we get to 0, the slope is 0, and also looks like we're going to have a concavity shift over there. So I think to make that work, we're going to have to round this out, kind of like this. There's going to be a concavity change here because the concavity is going to go from negative to positive. And then the slope is going to maintain positive over here between 0 and... the slope is going to remain positive between 0 and 2. Once we get to 2, the slope has to be 1. So why don't we draw a slope of 1 over here at 2. So we're going to have to match with that. Okay, so positive concavity and then increasing function. So, and then we're going to make sure that that slope matches. I don't know how convincing that looks. Let's start over again. And I'm seeing what I did wrong. The slope is 1 when x equals 2. So that's a little bit less pressure to get that right. Okay, so there we go. And then from 2 to 4, we're still increasing, but now we have negative concavity. Okay, so maybe doing one of these. Oh, I should also look at x equals 4. We have a horizontal tangent line as well. Okay, that right about does it. And then from 4 to 7, we have negative concavity and negative slope. So we're just basically coming straight down here. Always making sure that we have a negative concavity. It's not very convincing for negative concavity there, but that's basically what we should be looking at. I think I drew at x equals 2. Probably drew that a little bit too low, so we've raised that to right about here. Now this next one is crazy. Sketch a graph of the continuous function over negative 5 to 5, having a range from negative 1 to 0. So we're never gonna be up here. This section is going to remain blank. What else? For x greater than 0, the roots occur at every whole number. So whole number are those numbers 1, 2, 3, 4. 1, 2, 3, 4, and including 5. Great, that is cool. This is a even function, so that means we have a reflection about the y-axis. So if there are roots over here, then there should also be roots over here. And I think that's the last time we're going to talk about the even function until we're ready to draw the left half. So we're just going to concentrate on the right half now. So those are our roots, and so the function has to be down over here. The derivative equals 0 every k over 2. Okay, and then the first and second derivatives exist everywhere except at x equals k. And furthermore, we're always concave up. So what that says to me is that concave up and below the axis, halfway in between, we have a horizontal tangent line. So I don't know, maybe this will go like this. But in any case, this kind of looks like, well, like the curtains, drapery. So something like this. How far down does each one go? I don't know, and it doesn't really matter. So this is what I have drawn. We have horizontal tangent lines at every k over 2. We have a 0 at every k. And the next thing we're going to need to do is, or the last thing we're going to need to do is, this is a continuous even function. So the left side and the right side should be symmetric. So try as best as we can to make this look symmetric. Hopefully I'll do a convincing job. And then that's about as close as we can get. It's a crazy function. Not a whole lot to say about it. Okay, next function is not as crazy. We got a list of properties up over there. And first of all, h of negative x equals negative h of x. So this is an odd function, which means we're going to be symmetric about the the origin. As x approaches 0 from the right, we're going to go to positive infinity. So that's going to be easy. We're going to have to do one of these things. Approaching 0 from the right, we're going to positive infinity. As we go to infinity, we're going to have a horizontal asymptote. The y value is going to approach 0. Okay, for positive values, h is equal to 0 only at x equals 1. So we're going to have to cross here. And since there's no other place that's going to cross the axis, this has got to do this. Okay, and h prime is equal to 0 only at x equals 2. So at x equals 2, we should have a horizontal tangent line. Okay. And then for h equals 3, we have a concavity change. So we're going from concave up to concave down. And then from here on out, we're going to be asymptotic with the x-axis. Okay, so that is the entire positive side. Now the negative side's got to be the same except for reversed and upside down. So here we're going to have a, what is that at? About 2 horizontal tangent line, and then 3 and negative 1, or now positive 1. That's going to be our point of inflection. So let's draw this. There we go. Man, I like that better than the other side, actually. Right, so it's an odd function, hits all the qualities, and we're ready to move on. So for question 4, we got a graph now, and we're supposed to decide things based on that graph. So for x not equal to 0, f of x is symmetric. Well, it's not an even function. The left side does not look like the right side. Actually, the left side looks like the right side upside down and reversed. So that's indicative of an odd function, which means that we're symmetric about the origin. So if we're symmetric about the origin, that means f of x is equal to negative of f of x. Okay, so those are just some things that you have to have down and a little bit memorized. Okay, are there any places on the graph where we have a point of discontinuity? And I'm looking at the graph and I can only see a point of discontinuity right at the origin here. So there's my point of discontinuity. We have a point of discontinuity when x equals 0. Next. As x approaches 0, f of x equals, so what is the y value as x approaches 0? Well, on both sides of here, it looks as though the y value is approaching 0. So then the limit as x approaches 0 is also 0. Where are the zeros? Well, I can highlight them. They're there and there. Just in keeping with this, I think we're going to have to say that that's negative 5a and positive 5a. F prime does not exist at x equals. Well, here's a corner right here. The slope from the left and the right do not match. Of course, discontinuity, and since we have an odd function, there's another place. So that looks like at negative 2a, 0, and positive 2a. And then letter F, we're looking for when is f double prime less than 0, which would be the same thing as saying when are we concave down. So we'll go through each one of these pieces of the graph and we'll talk about it. Here, that part that's highlighted now, that has concave up. Concave up is shaped like a cup. Concave down is shaped like a frown. This is linear, so there is no concavity for that section right here. And this last section, this is the only place where I have concave down, shaped like a frown, right over there. So f double prime is less than 0 for the interval from 2a to 6. Okay, so that takes care of it. That's all of our section 5.3 concepts review. I'll see you guys next time when we look at more calculus.